Good evening, everyone. A very warm welcome to day 3 of our FDP, Modeling, Simulation of Composite Materials, Fabrication, Characterization, and Application. We are delighted to have you all back and look forward to another enriching session together. Have you ever wondered how a jacket light enough to wear can stop a high-velocity bullet? How much science and design thinking are hidden behind this life-saving technology? Today, we unfold these answers in our session titled Behind the Armor, Science, Design, and Impact of Bulletproof Jackets. And let me introduce the honorable resource person for this session, Dr. Hemant Chauhan. Dr. Hemant Chauhan is an assistant professor at Ahmedabad University, specializing in composite materials, ballistic testing, and automation. With a PhD from IIT Delhi, he played a key role in developing the ABHED bulletproof jacket for the Indian Army, one of the lightest and first indigenous solution in its category. His research focuses on advanced ballistic composites, ceramic polymer systems, and interfacial bonding strategies for multi-material protection. Recognized in the LIMCA Book of Records 2011 for creating a wireless operated unmanned vehicle, he holds 8 patents in composites, protective technologies, and automation. His work continues to advance materials testing and automated manufacturing. We are feeling privileged to get such a great academician as our research person. Sir, please.
Thank you. Thank you, Mr. Amit. I'll share my slide.
Yes, sir.
Is my screen visible?
Yes, sir. Yes, sir, it is okay. Fine.
Fine, visible?
Yes, sir.
So I have time till 7:30.
Yes, sir.
Okay. I'll try to finish it 10 to 15 minutes before, but if I'm running late, please do.
Okay, sure, sir.
Okay, fine. And shall we begin or we wait for a couple of moments? We are 140 as of now. I mean, as in participants.
Yes, sir, you can start.
Can start?
Yes,
Fine.
sir.
Fine.
Hearty good evening, sir.
Good evening, sir. Hello, everyone. I'm this side Hemant Chauhan, and I'm going to. Can you please once confirm my audio and video? I mean, audio and screen are.
So
Yes,
both
sir.
are good. Both are in good only, sir. No issues.
Okay, fine.
Thank
Thanks.
you.
Thanks for confirming. So we will have a short journey about, not just about, rather, the development of a bulletproof, and more important, what is done. Once you achieve, you land somewhere, it's a history. So what next should be, and what I can or one can learn out of it, and how to get benefited out of that, that should be the prime criteria. That's what I feel. So we will have a short scientific journey about how the bulletproof stuff goes. Okay. And before that, or in general, in a defense application, what matters, the materials or the manufacturing? Because in defense, we talk a lot of materials, but it's actually a function of material along with the manufacturing technology. When we see the modern world, gone are the days when we were dependent on conventional metals or materials which are high density and a constant strength. You just can't play much around. So in the defense world, lighter the better, because lesser the mass, faster the speed, and it has to be safer. So ultimately, defense is looking for a more efficient solution. And that always is the criteria for decision. And in that process, composites or advanced material, they play the strategic role and not the conventional materials. So that is where the defense thing actually becomes very, very critical, that we can have a material or a technology initially designed for defense or aerospace, and then it can come down to the normal world or the civilians low cost competitive kind of environment. So that is something which I would like to touch upon towards the end of my presentation. So what are the challenges we face? Defense generally depend on manufacturing capability, and it's not just about the R&D excellence, because in my journey I have faced few of the things that technologies fail more often at scale up, not at the conceptual level. So there lies a critical gap, that is my process repeatable? Can I produce consistently? What are the costing factors? Because at research level, we say that cost is not a criteria. But when we look for forces or aerospace, you have to supply consistently in terms of quality, quantity, and you have to be sure that it will last for the rated lifetime. So what defense need is a manufacturable design from day one instead of a technology which is on design table provable. But when we talk of scaling, we are facing challenges. So we need, along with that, that design is manufacturable from day one. We need a tight control over the manufacturing process, control, validation, overall the thought process of production, and that should be presented in such a way that it can easily be absorbed by the industry as a solution. So from this point, I would like to take you through my journey that at research stage, we can develop best of the materials in the controlled environment. A good quality sample for prototyping and initial testing of force can be done at academia, but ultimately when we are developing a defense solution, it has to go to field for the field testing or the military certification, what we call. So in Indian context, it would be DRDO. You can have an initial tie-up with armed forces or policing, but ultimately it is the DRDO certification that will matter. So we'll come to that as well. And then we have to, or rather, they certify that your product qualifies all the environmental or the service parameters as well. Even if academia and defense has developed something, the mass production will always lie with either a public sector or a private sector company who can actually absorb the technology reliably and repeatedly produce the same product in large numbers at cost competitive pricing. And there is a consistent chain of right from the raw material to the finished product with the traceability at each and every stage. That is something which is beyond the scope of academia. We can move from TRL 0 and 1 to maybe at the max 7. The 8, 9, that is field validation, goes to the actual user, that is military in this case, and mass production in any case will be done by industry only. So basis that journey, we found that the materials that perfectly often work in a lab environment, as they migrate to industrial aspect, the things changes significantly. So we need to work in such a way that the academia produced product are actually going to serve the nation. Fire. And this is my journey. So it's less than a second that the journey is over. Now, what all was involved in this journey? And before going into that, theoretically, as per the design, a AK-47 is supposed to fire 600 rounds per minute. Practically, the army people says because of friction and weapon barrel, bullet type, belt type, and whatnot, the practicality is 120 rounds per minute. Still, a AK-47 is firing 2 bullets per second. And if we have to protect a person from these 2 bullets, which are coming within a time span of 1 second, sorry, 2 bullets in a 1 second time. So it's quite a task. Why it's a task, you'll get to know very soon. Now, when this thing happened, that there is a sound of fire and some bullets were fired, three things happened. There is a term of internal ballistics, that is what is happening inside the weapon till the point the projectile comes into the atmosphere. External ballistics, what happens with the projectile when it starts its journey from the exit point of barrel to the final target. And the final target location, if you are trying to stop the bullet, then we call it as a terminal ballistics, that how you are going to handle this projectile. So what do we mean by these? Internal ballistics basically refers to what is happening inside the barrel. So what kind of propellant, what kind of ignition, what burst pressure, what is the length of the barrel, whether the barrel is a smooth or it's a rifled one. Those all parameters along with the aging of the barrel, they will define that what is the status of projectile when it leaves the barrel. So you can see a small handheld weapon versus a rifle. So the barrel length changes, the type of grooving and all. They significantly affect what they affect. They affect the journey of projectile, how it will travel in the air from this tip to at what speed, whether it's spinning or not, what is the angular velocity, the yaw and precision, what kind of trajectory it will take depending on the location on the earth. The gravitational field will have its own effect, what kind of air resistant and wind drift it is facing, and ultimately depending on distance. Now from the tip of the barrel to the end target, the distance could be few meters to few hundred meters. So accordingly, what kind of residual velocities at the point of impact we are expecting, and that this distance we call as the range or the effective range, where this weapon can effectively do its task. Let's call it killing a person in this case. So that is how internal and external ballistics deal with each other. I am more interested in terminal ballistics. That is the study of impact, what happens to that material, will it penetrate or not, and how we are going to handle this impact energy. So that is all about ballistic protection, or simply put, terminal ballistics. What are the key focuses in this case? Number one, prevent the penetration. If your projectile is penetrating your bulletproof material, the person is dead. Even if the projectile is stopped, what will be the deformation at the back of the panel, because it may lead to us, if the projectile leads to a significant deformation at the back of the panel, it can lead to, and it does leads to, rib cage brokerage, liver or heart or any other critical organ burst. So that ultimately leads to, even if there is no puncture in the human body, the person is about to die. And these are the versions of the army people whom I met, that the bullet was not penetrated into the human body, but still my soldier died. So those are studies which are not declared, but there are instances, and officially they don't put it in the black and white. Another important thing, so that way, if deformation, the deformation is something which we see after the impact. At the time of impact, we actually measure back face signature. What is the peak deformation? So from stress strain curve, we know there are two parts, elastic region and plastic region. Whatever material we are using for bulletproofing application, it will have its own elastic region. So BFD, that is after firing, when we measure the deformation at the back, we call that as BFD, that is back face deformation or trauma. But that is the answer when the material has already recovered back, elastic recovery part of it. So the combination of, at the time of impact, elastic plus plastic is going to be higher than only the deformation, which is only plastic part of it. So globally there are two standards. The US one says 44 millimeter is permitted, because the adipose tissue, or the tissue, the muscles of the human, of the person living on the earth, wherever it is the person is. So accordingly they have classified that for US people 44 they have sufficient mass here, whereas in Indian context we have limited it to 25 millimeters. So that is as per standards. You cannot have the back face deformation, that is elastic plus plastic deformation of your material, bulletproofing material, along with damage, cannot be more than 25 millimeter. Now that increases the challenge, even if the penetration is stopped. And then you have to either absorb or dissipate. So either there is a ductile or a brittle failure, you can say. So either you are going to dissipate the energy, as in shattering of glass, or you absorb the energy, as in distortion of a ductile material. Historically, the things begin with materials like naturally available one, silk and leather. Gradually, the world moved to steels, It was in 1901, and this image, the 1923, this is considered as the start of the modern world of bulletproofing materials. In between, we had aramid after the steels, and present date we have a combination of a very complex composite system depending on threat level, the speed, the projectile we are dealing with. So that is what we are going to discuss now. Now, coming to the standards, so NIJ 0101.06 was the one when we started the journey. This was the standard. Last year, the 07 has come into existence. But more or less, thankfully, the weapons remain the same. So NIJ is basically considered as the gold standard. And nearly half the globe follows NIJ till 2018 end, nearly towards the end, or more than half the year of 2000. India was also following the same. Towards the end of 2018, Indian government came up with the BIS standard for bulletproofing. So we'll discuss that later. Over here we see that they have classified them into 2A, 2, 3A, and then 3. So this is a NATO standard bullet 7.62 cross 51 mm, which is a lead filled projectile. And then they have APM2, that is a US sniper. Whereas in case of India, we have a Russian Dragunov over here. There it is APM2, and here they have a lead core, where in case of India we have AK-47 with hard steel core. So the key things of relevance in any table are like what are the speeds and what are the mass of the projectiles and what is the maximum permitted BFS, back phase signature. So here you see 44 mm and how many bullets at what angle are to be fired. In 2018, BIS 17051 came into existence, derived mostly from NIJ, of course. So it aligns very well with that, with the specific requirements of Indian forces. And now, if you have to, one has to supply in Indian market any kind of policing or military related bulletproofing system, then they must meet the BIS. And in fact, the army requirements are even higher than that. So I'll discuss that now. So this is the key table which tells what kind of we are looking or we are dealing with. So at level 1, we have a pocket held weapon, what we call as a pistol or a SMC, a 9 cross 19 mm bullet. The weight is typically 7.5 gram. Full FMJ PB is that full metal jacketed lead core fired at a speed of and from a standard distance of. Then at level 2 we have AK-47, and at level 5 also we have AK-47. So this we will come later why there are two AK-47s with a slight velocity change, 710 meters versus 700. Then you call it bolt action, SLR, and there are globally multiple weapons which can fire this NATO standard projectile, that is 7.62 cross 51 mm. This too is a lead core, whereas AK-47 above this is MSC, mild steel, and below one is a hard steel. At level 4, we have a weapon derived out of AR-15, which is a US weapon. In India, we have the one developed by DRDO, that is INSAS, that uses 5.56 cross 45 mm projectile, whereas all others are 7.62 mm, which is a global standard. And the largest one, the projectile that can be fired by an individual using by a person only without any mounting or without any vehicle or tank or chopper in picture is a Russian Dragunov, that is 7.62 cross 54 RAPI, that is armor piercing incendiary. So it was primarily meant for puncturing the fuel tank of a tank. That's why it's called as armor piercing incendiary. So it has got a sparkling thing, basically magnesium phosphorus combination. So it is supposed to pierce the fuel tank and then ignite the fuel. So you need not have to bother much. The vehicle itself will burn out of it. The highest speeds, if we see 890 for INSAS, though it's still not lethal, and otherwise 830 for sniper, and for 751 it is 840. The standard testing distance is 10 meters. So we know more or less there are 5-6 weapons to be handled. Sorry. That's not the case. Though we cut it down and we see what all is there. But if I take only one, that is AK-47, so there lies the difference. Mild steel core has got a hardness of maximum 25 HRC, whereas a hard steel core of a AK-47 will have a hardness of 50 plus minus 5, which is way harder than your mild steel core. So this is the difference between a level 2 BIS and a level 5 BIS. And when we talk of a sniper, it is 65 plus minus 1.5. So the things are getting more and more critical. If I have to give you an example, where can I see this? So any mild steel will qualify this thing, a slightly better grade of, but still you can make a scratch on this mild steel thing. If I talk of this hardness, you take any automobile, pull out a shaft, even if the automobile is 50, 20-year old, if you pull out the shaft out of that vehicle, it might be black, but you can't create a scratch on that. And that is 45 plus HRC. Now imagine 65 HRC, which is way harder. This is just one of the parameters. Then we have a variety of shapes, sizes, materials, hardness, firing parameters, the type of explosive being used that will define the velocity. The rifle will define the bore type, smooth or rifled, if rifled, what kind of. So there are so many parameters to be handled. Still, finally, we know that, okay, there is one for this and one for that kind of, still a no. Now, this was just one of the random discussions. So that company, one from the Europe, they said, no, right now we have 7 options, whatever number you require. Now, all these bullets can be fired from AK-47. And we can see there are 7 different types, each one having its uniqueness. So that is where the game becomes more and more complex, that how to deal with this kind of a scenario. And then coming back to the BIS thing, so these are the standards that how much body coverage should be there. So I'll take only one of the parameters. Let's say the front, that is the chest of a medium size male. Then the BIS says that the requirement is 735 centimeters square to be taken care of. But Indian Army demands 1000 centimeters square. The BIS says 6 bullets to be fired, but Indian Army says for AK-47 you need to fire 8 bullets on 1000 centimeter. And for sniper, global requirement is minimum 1 and maximum 3 bullets, but BIS says, or the Indian Army says rather, 6 rounds to be fired. So that makes the game more and more complex. Going to the rest of the world, you have European standard, you have NATO standard, you have Australia, New Zealand, Europe, Germany, and so many standards. It simply means so much of variety. And whenever there is a variety, it is from the both the sides. So I call it as a virus versus antivirus. So we are the antivirus developers, the protection side of it. But then the science is also growing in the direction of killing machine. So there they keep on enhancing the or trying to speed material change. Material change is one of the thing which is very easy, because your outer cover will always be a combination of some copper brass thing. So you can never know that what is the actual hardness and what are the actual inside parameters of the material. So the key requirement is that my armor must meet this impact of a projectile, which I don't know what is inside. And we have to ensure that the back face deformation and back face signature is well within the permitted limits. Otherwise, you are out of business. So there is a constant need of technology improvement as the ballistic standards and weapons grow. So does should my jacket grow. Now, talking of the weapons, this is the smallest bullet. And before we enter into it, let me tell you that a blow of 25 to 150 joules on a human head, properly placed, is sufficient to kill a human. The smallest of the weapon, this is the one which you can see anywhere, a pistol on the back of a policeman. He is having this restricted bullet, what we call as 9 cross 19 mm, fired at 430 meters per second. And even that is producing more than 650 joules, so sufficient to kill. Talking of AK-47, that is 7.62 cross 39 mm, the energy is much higher. 6 or the NATO standard weapon, it is above 3000, and the highest of all is a Russian Dragunov in context of Indian market, because we call in Indian context this as the sniper, not the US one. So the weight goes slightly higher from 7.5, 8 to 10.5 gram max, and the kinetic energy is somewhere like 3600 joules. Whereas one sufficient to kill a man is somewhere around 150. And now the Indian Army is demanding that no, don't stop just 3 bullets, stop 6 bullets. So that makes the game very, very difficult. Further adding to that, you can take a screenshot if required. So I attended one of the lecture and I found that this is critical. So I've created this thing. So when we see AK-47, it is producing a rotational RPM of 2900 plus per second, not per minute. So, or you can round it off to 3000. So 3000 RPS is the rotational spin of a AK-47 bullet. Now imagine this as a grinding phenomena. So your bullet is actually a hard material inside and it is rotating at such a high speed, and your armor plate is actually a static member. So it's actually a tool grinding phenomena which is going to happen, but in a very short span of time. So this parameter particularly plays a significant role, because the spin will ensure that the muscles get entrapped in a circular fashion. So even if you are trying to safeguard a human, it's really very difficult apart from all the parameters mentioned here. So what is the solution, or how to come up with the best possible solution? The best possible solution can be some advanced material like composite, where when two becomes one, they are stronger than both of them individually, and what we call generally as a fiber plus matrix. That is a high strength unidirectional kind of a material with a homogeneous isotropic polymeric material. That way we can make a judicious combination to come up with a solution for high strength application, not necessarily along the axis of fiber, but perpendicular to that. So fiber will give me strength and matrix will ensure the shape is retained properly and there is sufficient addition between the two, so that we come up with a a composite system wherein I can design the strength of the composite. And this is what I call as the design triangle, that I can design a material somewhere less than the fiber strength and much higher than the metric strength. Now, depending on what kind of behavior I want it brittle or ductile or in between, what kind of modulus and what kind of deformation. The design table is yours, so you can design any material within this regime, which otherwise is a very, very difficult task when we talk of the conventional materials. So that way composites gives us a freedom. Knowing this, what all options are there? So since we have 6 types of bullets, let's now from this point we will limit ourselves to only BIS. So we have a 9 mm bullet, and then all others are rifle. Rifle we call as, or a small weapon we call the one which can be kept inside the pocket. 9 mm is the only weapon, a projectile, a bullet belonging to 9 mm will be fired using a weapon which can be kept in the pocket. There are weapons which are slightly longer than that as well. All others are rifle. So in that case, a soft armor panel is sufficient to stop the small bullet, but a hard armor panel is a must when you are firing a bullet using a rifle. Now, what all parts will be there in a typical bulletproofing panel? To ensure that back face deformation is well within the limit, we require a soft armor insert, which will ensure that the deformation, the BFS thing, is to be taken care by this material. And this should be sufficient to stop a 9 mm as well, the yellow thing. If there is a rifle bullet, then we require multiple things. If it is a mild steel or lead only, which is a soft material, only Kevlar or UHMWP, ultra high molecular weight polyethylene, is sufficient to stop the projectile. If your bullet is harder than this, that is, it has got hardness much larger than the mild steel thing, then we have no other option but to incorporate a striking face material. Now, this can be HNS high nitrogen steel or a high hardness steel, armor grade steel, but steel will increase the weight of the panel. So we migrated to ceramics. Now, this can be a silicon carbide or boron carbide or any other type of. For bullets, we prefer silicon and boron combination only. Then joining these two materials in itself will be a critical task, and making single unit out of it, that is a cover kind of a thing to this. Ceramics being very good under compression but very poor in tension and bending, you require a special type of protection in front of it. So that way, joining these many materials becomes more and more complex. The backing matrix material will have its own surface energy. Ceramics are much different in terms of surface energy and finish. So joining these two requires a lot of technological parameters to be taken care of. If you are using any kind of rubber or foam, they have a different type of properties. The frontal protection thing is going to be altogether different kind of materials, and we will simply say that it is a hard armor panel. So that makes the overall picture quite a difficult game. And each component is serving a specific purpose here. So this way we end up having more than one type of adhesive, at least I can say in this short span of time, that for my fibers joining, we have some adhesive. From fiber to intermediate material, there is another adhesive. That intermediate material to ceramics, I require another adhesive. And maybe there is an outer cover that will require another adhesive. Now I can have a single adhesive doing more than one task. Still, I require more than one options. So their interaction, how they deal in terms of compression, shear and tension, all properties are to be evaluated precisely. So we understand conventional were heavy. FRPs are better because of the high strength to weight ratio, corrosion resistance, much more comfortable because of the lightweight. What are the material options? We all heard of Kevlar a lot, but Kevlar to me is a history now, because when it comes to the major material for bulletproofing, Kevlar has got two major challenges. Moisture, water is a major problem to the Kevlar, and UV rays deteriorates Kevlar badly. So though Kevlar is very good at energy absorption, it is primarily meant for ballistics bulletproofing kind of application. But now we have a better version, ultra high molecular weight polyethylene, density 970, so lighter in weight. A panel made out of UHMWP will float in water. So my bulletproof jacket serves both the purposes. It is a BP bulletproof as well as it floats on water. It is ductile in nature, so the fibers get stretched. The mechanism of energy absorption is entirely different for the two worlds. In this case, whereas in Kevlar, it is a stretching followed by fibrillation or energy dissipation in a different way compared to how the UHMWP deals. And then we have hybrid of, that is combining the best of both. So how we are going to, that I will discuss later. So with the combination of the material system, we can have an improved energy dissipation and optimize the back face deformation. That way we try to increase the survivability chances of a person wearing it. Now, before going into that, we should try a simulation model. So for this particular Abhed bullet proof, we opted for LS Dyna because that is the best for the solution. So this was the final model wherein we are firing a 7 hard steel core AK-47 bullet at 700 meters per second. These first three cells, they are resembling boron carbide, SiC ceramic, and the color changing things, they are ultra high molecular weight polyethylene backing made out of. So this side it is compression molded and that side it is pure ceramic, and then joining these two. So we created the model and we found that, or optimized that, the bullet velocity can vary in what range. So right from 650 to as high as 800, because the AK-47 speed is 700 for level 5 and 710 for level 2. And in Indian context, we always have plus minus 15. So 725 is the highest speed At 735, we have designed that the tip will get exposed. The bullet is not penetrating as such, but it might be visible at the last. Less than this, any value, your bullet is well within the composite. At 750, it is penetrating, and at 500, for the same set of parameters, it will actually perforate completely. So these are the instances at the various time units, and the kinetic energy available with the projectile after the completion of this much time. So we see that after 0.04 into 10 to the power minus 3 of a second, the 800 meter per second bullet will still have more than 100 meter per second of this energy. So this is in terms of, yeah, joules of energy. So this is still a lethal one, sufficient to kill or significantly damage a human. Whereas as we go down, the kinetic energies are nearly zero. So for 715, it is zero. So we are having a very good model. So for this case, we have used LS Dyna. Abacus is equally good, but for bullets and these kind of events, LS Dyna is preferred. So we have been into that. But this problem is not that simple, because in the previous slide, we have seen that one bullet is handled, but in reality, as per NIJ for AK-47, you are going to fire 6 bullets. So in simulation, you have to fire 6 bullets and one after the other. The material will get sufficient time to recover. A bullet is fired, we see the panel, take it, turn around, whether it is perforated or not, set the system for the next round. In the process, typically 8 to 10 minutes are gone. In simulation, we are firing only one bullet. So your panel is intact. But after one bullet, what will be the level of the panel? What kind of damage and delamination has happened? We don't know. So this is what happens when a single bullet is fired. The bullet is stopped. But what is the condition? And this we done explicitly to see how these damages and cracks go. So there are many unanswered questions in case of simulation, because simulation will limit itself that, okay, the bonding is perfect, the delamination will follow a perfect mathematical rule, which might not happen in the real world scenario. So for that, what all ballistic materials we are going to use? The backing side of it, that is the soft side, ultra high molecular weight polyethylene, and before that it was Kevlar. PBO is a very good fiber. It came up as a game changer, and very soon it was observed that environment is an enemy to it, so it won't last long. Whereas when you made a bulletproof, it should survive for at least 5 years. So if we look at the modulus to tenacity, tenacity is a textile world term which basically deals with the tensile force per unit linear density corresponding with the maximum breaking force. So we see that steel is at a very low level and we have no options to change it. The glass fiber is at much higher value and the Kevlar has reached the limiting value. So this is the zone of Kevlar and it cannot go further. The spectra term basically refers to a specific grade of ultra high molecular weight polyethylene by Honeywell Advanced Material. So they started with spectra 900, and as they increase the molecular weight of the PE fiber or the PE granule, this thing is moving up. And I'll come back to this, that what do we mean by this. So as the time grows, as the polymer chemistry research is growing, the modulus to tenacity ratio, this arrow is constantly moving up. And that is where the polymer designer is getting more and more important. And so is the mechanical or the manufacturing guy who's going to use this fiber or this kind of a material system. The key features which make UHMWP a unique one is its high strength, high fatigue, excellent chemical resistance. Polyethylene, everyone is using, I assume, in a day-to-day life. A simple polyethylene, it's only that it has got a low molecular weight. Then we have LDPE, low density polyethylene, high density. Then there is an intermediate, and finally comes a ultra high molecular weight. So they have got excellent chemical resistance, lower in density, and by varying the manufacturing process, it can lie somewhere between 0.93 to 0.97. This is the highest one can get with the UHMWP. So in any case, your BP is going to be a floating body. It's never going to sink in a water. They've got low fiber to fiber friction. In case of, say, glass, the fibers interact and they abrade each other, or many other fibers as well. They interact with each other, but since they have low surface energy, they don't interact, or they give very low friction. So no damage. Not much affected by UV. That's a very good advantage. They are viscoelastic in nature, low in dielectric constant. For this reason, now I've started studies on that direction. It's a very good material for these unmanned aerial vehicle, the drone body parts, or wherever we are looking for the radar transparency. And these are polyethylene. I hope you all know very well. We use polyethylene for waterproofing purpose. So they are hydrophobic in nature. So that way, plus they have excellent tear resistance, good abrasion resistance, good cut resistance, chemical resistance, and above all, the best is the ballistic properties of this particular material are highest till date. With that, we have an open field that we can develop even better a material. The only issue with the UHMWP is low melting point. Polyethylene, we all know you are increasing the molecular weight. You can't change the melting point. And being plastic, don't expect very high hardness. Yet, multiple layers of this material can successfully defeat lead and mild steel core bullets. So that is a good feature to us. Talking of the moment we have to migrate from soft core bullets to hard bullets, that is HSC or sniper, you have no other option but to place a higher hardness material in front of this polymeric backing. So homogeneous material with very high compressive strength but very low strain to failure is an option, and that is where ceramics come into picture, because we are not interested in metal for the weight penalty reason. So normally we have ceramics in the form of powder, and then they are suitably processed to give us a tiles. Now this can be a monolithic tile matching the dimension of your BP panel, or they could be in the form of multiple small tiles, mosaic tiles. They are to be placed on top of. So in my case, let's say there were 107 small tiles which are to be placed on a compression molded UHMWPE panel. The aim basically is to get good ceramic processing so that we can successfully defeat these 6 to 8 projectiles of high hardness. If not done satisfactorily, then your fourth onwards bullet will perforate the laminate. And the best of the ceramics are boron carbide, silicon carbide, and aluminum oxide. Though this one is preferred for blast, it is not preferred for personal protection because of its low efficacy compared to these two and higher density compared to boron and silicon. Now, what makes and how the bullet stops? So in case of ceramic, as we all know, ceramics are brittle in nature. So the projectile damages ceramic targets as it's the leading surface, and it will try to push out the ceramic material. Now from at this point, I would like to connect you back with the grinding phenomena. So your projectile is coming at somewhere around 2900 plus rotations per second, revolutions per second, and you have got a grinding wheel which is right now static in nature. So your bullet will give both the linear motion as well as the rotational motion. So in this case, this ceramic should abrade the bullet. The first thing will be abrasion. Then because of the high linear velocity and high hardness of the projectile, a high hardness material will always break into two instead of getting a ductile deformation. Ceramic will make sure that along with the damage of the ceramic, the projectile is also broken. Once your projectile is broken into more than one part, you are going to handle multiple pieces, but thankfully at a lower kinetic energy, because the initial kinetic energy was a constant number. Now it is broken down into multiple pieces. So handling becomes both easy as well as difficult. If it is broken down and before that the tip has been eroded very well, so there is only a blunt part. Handling a blunt part is much easier than a ogive nosed high hardness material. So that way we are going to play with that material system system here now as both the parts, projectile as well as ceramic. So what happens? What is the mechanism behind? As your high hardness projectile will enter into the ceramic thing, a damage zone called as mescal zone will be created. Initially, it will try to push the material. As an outcome of that, there will be an extension or tension at the back of it. And we all understand with a cup of tea in my hand, ceramics are very poor in tension. So if there is not a sufficient backing, it will fail very comfortably. And that is where the role of a backing comes into picture. That we require a very good backing which will take the energy and do not allow this tensile deformation. Otherwise, my ceramic has already cracked. So that is the first thing. Then we have this projectile will try to compress or try to push away the ceramic thing or the material in front of it. That will lead to the formation of or breaking down of ceramic tile into a powder. We call it as a comminution of. Because of the high shear stresses, the solid tile is now being converted into a grinded powder kind of a thing. And then there is a high pressure which will try to extrude this material on the sides, and the projectile will keep on moving further down. So this entire mechanism will actually ensure that the energy is absorbed, the projectile is grinded suitably, it's broken down, and if baking is sufficient, my ceramic will retain its position without giving way to the projectile. If this does not happen, then we are going to face a challenge. In another study, they mentioned that this is the comminution zone. The crushing will happen in front of the projectile, and there will be a crack growing from the tip towards the back, and this is where we see the tensile deformation of the ceramic. If this tensile deformation is allowed because of lack of stiffness of this composite backing, then your crack will grow very fast, and in that case the projectile will enter, and there will be a shear plugging phenomena happening throughout the object, because in any case this composite backing has got no strength or no hardness to actually deal the hardness of a hardened projectile. To further study this, flashing X-rays were used to observe that how the radial and circumferential cracks grow. So here we see that if we take a single piece tile and fire a AP round, then we are getting some specific pattern of a radially outward and a circumferential circular kind of the cracks. So we see that if I take a second shot and by mistake it happens to hit on this, let's say this character C, which is a crack location, then this second bullet is bound to penetrate this panel comfortably. So that led to the decision that monolithic tiles are only applicable when we are firing only one bullet or at the max 2 to 3 bullets. But if we are going to fire 6 to 8 rounds, then these kind of radial and circumferential cracks will make the life miserable for the composite designer or for the bulletproof panel designer. So, and then these are the high-speed X-ray flashing imaging, that how APM2 interacts with the ceramic thing and how what kind of deformation is happening in front of it if the bullet is stopped. So we decided with a Y junction kind of, so a hex kind of a tile versus a quad kind of a tile, and we found that since in case of hex tile, we cannot give a curvature at the back of a human body, a human chest has got a curvature of 400 R. We cannot provide this radius to this hex tile and we want to optimize the weight. So quad is a much better option. Though both will have same problem, there will be a star formation over here. So if bullet hits here, how you are going to handle it, it's critical. Here it is in the form of T junction. So it's a Y junction versus T junction. But since I can give a radius at the back of a rectangle, so these were turned out to be a better option. This particular thing is a boron carbide tile. So it has got a modulus of 450 GPa and density is 2.52 to be specific. UHMWP we are using in the lamineiform. So you have unidirectional fiber. There are two global masters basically. Earlier it was Dyneema and Honeywell. Now the Dyneema is taken over by Avient. So we have Honeywell Advanced Material and this Dyneema thing. Now, before going into actual panel manufacturing, we need to understand, shall we rely upon the properties given by the UTM machine or not? So for that, should understand what is the rate of loading or strain rate. So it is this low. I won't go much into this for the time reasons. This thing is the location wherein we have a quasi-static testing and we call it as a UTM, where we test it, where inertial force, that is the effect of mass, can be neglected and time is sufficient that event can be considered isothermal. But the bullet is somewhere over very high strain rate of loading. The rate of loading or shear rate is the rate of change in strain of a material with respect to time. So I've designed and developed a high strain rate test mechanism, what we call as a split Hopkinson pressure bar. And on this, we try to evaluate the properties of materials under the state of impact. So first we should understand the quasi-static properties. Testing a material like UHMWP is really difficult because it is a very slippery material as well. So you can't easily grip it. So I designed a special gripper mechanism for this. And then we tested what I call as generation 1, 2 and 3. In the next slide, I'll show you what is 1, 2 and 3. So Spectra is by Honeywell and Dyneema is the other company. So these are the stress strain curve of these materials and you can see the gauge section of these materials. Typically, the strengths are somewhere between 800 to 1400 megapascal as per my testing. And we found that as the generations grow, the GSM, that is gram per square meter, generally you come across this term with respect to paper, the GSM is going down and strengths are going up. So that is the beauty of UHMWP and how the tenacity is helping us. So in future we are expecting that there will be a term of fourth generation and the strengths will go even higher and the GSM or the weight per layer will go further down. Now, this is the typical mechanism of a split Hopkinson bar, wherein a striker hits a homogeneous material. As an outcome of that, a compressive wave travels through this particular bar, and we have placed the specimen at the center of it. So, depending on impedance mismatch, which is a function of density times velocity of sound in a material, the reverberations of this stress wave will happen and we will have a reflected and a transmitted wave, and these three waves, that is the incident, a reflected and a transmitted, they will tell us the material properties. And for that, we have some assumptions that everything is in place and correctly, because we are not doing things in a three-dimensional world, but in a 1D phenomena. So if this is the case, then this is my incident energy, a reflected one and a transmitted one. We superimpose them and using a mathematical formulation, of course, this is a strain gauge data, it has to be suitably converted. We can measure the strain rate, average value of strain and stresses. So that way we can characterize the material at high rates of loading. And this is how the event goes. Okay, this video, I'm not getting it. Anyways, we'll move on. You can see elsewhere. So how this thing helps us, that this is for Kevlar. Kevlar polypropylene, we observed that Kevlar fiber remains the same. Under the UTM, the strength is for this particular specimen is more than 1000. And in the high strain rate regime, though the numbers are growing, but compared to quasi-static data, these numbers are low. As the strain rate grows, the strength seemingly increases. Now, if for the same Kevlar polypropylene, this is Kevlar 129, if I change the matrix from polypropylene to polyether amide, which is a very hard and brittle material, polymer, your quasi-static data has gone down and the high strain rate data is still constantly moving up as we move from somewhere around 2000 to 4000 plus kind of a strain rates. And similar studies, if someone is interested, aluminium generally is an energy absorbing ductile material. But if you wish to make a brittle material, that is something like a glass which will shatter, so under the high strain rate regime, I can design both. Now, this is my aluminium specimen with high hardness particles. It is not deforming. If it is pure aluminium, it is deforming very well for the same impact energy, and with the help of suitable additives we can make it brittle as well. Brittle is not equal to a poor material. It simply means energy dissipated. So my glass will shatter down, but ultimately will take away the energy of the projectile. So we also did the simulation of this, and we tried to figure out that if we can perfectly match for UHMWP. So close to 5,000 we performed the experimentation, and we found that simulation results are more or less exactly matching with the experimental one for UHMWP. These are the first generation materials wherein there is a elastic viscoelastic zone followed by a constant plastic region, whereas in generation 2, now when I say generation, it is not by us but it is by the Honeywell people, that they developed the better version of fiber or the overall composite system lamina. So there is a elastic as well as plastic, there is a constant growth in the stress, and the present generation is even better than that, and this is where moving from 250 plus GSM to we have come down to 144 GSM, and your material properties are constantly improving under the high strain rate loading. Now, how do we manufacture a laminate out of it? So for UHMWP or for the composite part of it, compression molding turns out to be the best possible option. So compression molding is a standard process wherein we place the desired number of layers inside a lower platen, which is a hot surface, and there is a upper platen as well which is also hot at the desired temperature, let's say 100 degree or 130 degree depending on the polymer properties or the matrix material. We close this, apply the rated pressure for designated time along with the vacuum, cure it. I won't
Hello,
go
friends.
into this video.
Welcome to
I don't have time for that. The key things out of this compression molding is that, okay, we have devised the process and that is good enough. No. There are so many variables that can comfortably affect the final outcome or that will lead to the ballistic properties variation in our case. So if I change the molding pressure, so we studied this, the pressure was in PSI though. So 34.5, if I make this molding pressure increase by 4 times, the same composite laminate is giving me a strength of somewhere around 450 to 600 MPa. Simply by increasing the pressure, let's say these are 10 layers. So my 10 layers were resulting into 445 megapascals of strength in compression. By increasing the molding pressure by 4x, my properties are improved significantly. Then we have number of layers, the time, the molding temperature, and on we can have with a given machine a variety of ways to deal with the material system, so we can play with the properties of the same material. And then this is a quasi data. Again, in high strain they will again vary. If my compression molding is done imperfectly, I can do a non-destructive testing called as ultrasonic scan. So you have got a scan, a B scan, and a C scan. So this particular thing is the throat panel. That is, this portion is to be protected from the rifle threat. So this is a hard armor panel meant for throat protection. And you can see a lot of reds and loosely white or less blue kind of spacing. Whereas in this case, this is a perfect one. So this panel is a perfect one, and this one has got so many. Since it is not densely packed, it's a defective piece, bullet will perforate, let's say, these 100 layers. So in this case, the bullet will perforate, and in this case, at least from the result of NDT, we can say that most probably this is supposed to stop the bullet. If your compression molding job is perfectly done, you have the right ceramic with you. So in that, we can move on to integration of ceramic in front of UHMWP. So for that, you will require an autoclave. So we have got our compression molded panel. Then we have the ceramic tiles. We place them on top of this UHMWP panel, cover it with a different material that is for the impedance matching property so that it behaves in a better way. So we have been using Kevlar in this case, and then we wrap this UHMWP back ceramic front with a Kevlar. And this is where you can see, even if I say three terms, UHMP is a low surface energy system. Ceramic backing is the one part which will interact with UHMWP, and Kevlar is altogether different, which will wrap this entire thing inside. So I need at least two different kind of adhesive, and this is a typical autoclave cycle that along with time we keep on increasing the temperature and we apply the desired autoclave pressure. I am assuming you are known to compression molding and autoclave. And then once we are ready with the panel, whether it is purely UHMWP for mild steel or lead core bullet, or for hard steel, a autoclaved panel, we go to a gas gun. So this is a facility which we've developed at my alma mater, wherein under the single roof we have got the design, manufacturing and testing. So this is a gas gun shot. Now this should run. So this is the simulation running. And here you can see the bullet of AK-47 firing upon the panel with a high-speed camera. And this is the debris of the ceramic. These all black particles are basically the boron carbide particle. So ultimately what you are producing is a UHMWP backing, and on top of that you are going to have a boron carbide. So with this kind of a thing and then wrapped with a Kevlar. This is just for your better understanding of how the things are. So by this we developed BIS level 2 and 3. This is how the panel looks like, meant for 8 rounds of AK-47 or the BIS level 3 MAT ball. And this one is the type of panel which is made for BIS level 5 and 6, that is AK-47 and sniper with hard steel core projectile. Is this sufficient? No. These panels are to be tested against thermomechanical conditioning and wetting parameters. So you have to make sure that because of moisture your panel is not damaged. So different standards have got different times you have got to. So we provide a sealing to this panel, and then this panel has to be dipped inside water tank at least more than 100 or 150 millimeters. So there is a water head requirement. In case your pouch is punctured or your material is affected by moisture or water, it will serve as a lubricant and your bullet will perforate like anything. So if this is made out of Kevlar and you touched water to the Kevlar, there is no need to test the panel. It's bound to fail. Then in thermomechanical conditioning, there is a 11-day cycle, at the end of which 11th day, your panel is equal to 1 year aged, 5-year aged panel. So that is basically the aging cycle for a hybrid panel, that after 5 years also it should stop the bullet. And this is how we test it. So in the defense, TBRL Chandigarh does it, but in field I've got this thing tested so that I can explain. So this, the tip of this rifle is at a distance of exact 10 meters from the panel. We are going to place the panel, and this is a velocity measurement system, and this is the overall scenario. So here is my panel, the distance, and we place the high speed camera for better understanding. If the bullets are stopped, and if it is a soft bullet, mild steel or lead, then you will get lead will get disseminated into powder kind of a thing. Not necessarily a one-piece bullet, could be not. If it is a mild steel, then how far it has gone, we try to look at it, that how the damage was, till what depth the damage has happened, because these are the parameters which are not just going to tell us that okay, the bullet is stopped or not. That's fine, it's stopped. But how we are going to come up with a better technology, a better solution, the next version of it. For that, we do the operation analysis. If it is a hard steel core bullet, then also we recovered n number of AK-47 fired, and you can see in this image the left side all are smaller and right side all are larger. So we performed an analysis and found that this is the safe zone. By knowing the weight of the remaining core, this is the original core of a AK-47 hard steel. If the weight is less than this number and the length is less than 12.5 kind of remaining length, then your bullet is stopped, else it is perforated. So we developed a correlation basically, and erosion is primary, whereas in the previous slide, the mass will remain constant. Not just the destructive, we do perform a lot of non-destructive testing. So CT scan is one of them, X-ray or CT scan. So here is a tested panel of AK-47. I would like to show BIS level 6, that is one tested with sniper. So here you can see the shining white part is your ceramic and the backing is relatively grayer, is the UHMWP backing, and these are the 6 shots. So 1, 2, 3, 4, 5, 6. They are not telling that bullet is stopped. That's fine, bullet is stopped. Where exactly it got trapped? What was the total deformation and how to improve upon this is the key result we are looking from once we have stopped the bullet. So these are the finally tested panel. These are all 2023 job which is done. So you can see mild steel core AK-47, the front, the back, all bullets are stopped. Fire. And this is how the next journey was, that we have a burst fire phenomena wherein 3 bullets are to be fired, but humanly it is not possible to fire 3 bullets on 1,000 centimeter. So I used to get 2 riflemen. So 3 bullets are fired, but 2 are on the panel, and remaining 2 are also on the panel. So in total, we are firing 4 bullets in a short span of time, and using a high speed camera, we observed what happens. And these are the 4 bullets, and at the back, you can see there is no perforation. Now this time of 0.029 second is the key. The second bullet will come after this much time. Before it could handle that 3000 plus joules of energy, there is another 3000 plus joules of energy. And within the next that much of time, we are going to get one more such shot. Fire. And then a variety of panels and variety of projectiles. So the same thing was also done with this 7.62 cross 51 mm. And then we all to study, just a moment. So this one shows that what happens with a 9 mm bullet, and this will happen inside the muscles of a human body if we assume it to be like that, because this is something like a piece of cloth, and these are the back of these panels where we see that there is no perforation. So this is the technology which we could deliver to the nation, that equivalent to NIJ 06 as per BIS level 6. That is, instead of 3 bullets of sniper, stopping the 6 bullets, and as per BIS level 5 jacket, that is, instead of 6 AK-47, stop 8 AK-47, and others lower ones are always a comfortable job, and meeting the requirement of Indian Army's GSQR of 1707. When we started this journey, the threat level was, the solution by DRDO was at 10.4 kilograms. We could bring it down from 10.4 to 8.2 kilograms, and there was no solution globally available for sniper meeting the requirement of 6 rounds. We could develop the solution weighing 9.5 kg, which is even lesser than what we were at for level 5. So this technology is presently under transfer. The public sector company has taken it as Medhani, and there are 2 private players who are absorbing this technology. So that transfer is in progress while we are discussing here. These are few of the glimpse of wherein we are presenting to the national and the cabinet ministers about this particular thing, which is delivered to the nation in December 2024. So, and a lot of media coverage was there for this thing. We don't have time for that. You can come to that later. The lessons learned from this body armor story were: best material is not necessarily equal to best product. System integration will matter more than the individual property, and that is something which academician and researchers will have to take care right from the day one. It's integration over the peak performance that matters. So designing, layering, assembly, make sure that it is effective in the real world scenario, and testing and validation are ultimately the key, because you might be claiming anything, but it's the defense department who will clear your product for the desired task. And cost along with the repeatability is more important than once in a while a rogue a peak performance. We have to make sure that that lab scale project, even if it's a slightly lower properties, if can be produced in masses, is more important than once in a while kind of a phenomena. After that, I had a next journey, but I'll be moving slightly faster on this one. So parallelly, a friend of mine joined Ireland, University of Limerick, and he used to share the similar things that goons are hitting the policemen. So I thought Europe is a better place, but he had a similar newses over the years. So we planned that why not to, or rather the police department was looking for a solution. So the next challenge I took was that with these traditional limitations, we need a specific set of machinery for this, which is quite a costly affair. And in European world, their prime target is money making. So they are more interested in aerospace related research than the defense related research, because of the lesser number of population and lesser number of challenges across the borders. So we thought of having something new, and there they have a unique kind of a thermoplastic resin called as, or commercially termed as, helium. So being a thermoplast available in the form of liquid and is recyclable, is ductile, so we thought of developing something out of it using the available resources at the university, which are not directly related to the defense kind of manufacturing, the type of machinery we look for. So using a simple RTM or VARTM and using the liquid thermoplastic helium, which is recyclable, repairable, easy to process. These are the properties of the grade of helium which we used. And then we studied a variety of 2D, 3D woven fiber types. These are 3D woven, the previous one were 2D. Carbon being not a primary ballistic material, we studied both basalt as well as carbon. Since they didn't had a firing range, so I helped them design a one with the police department. They call it as Gerde, and their primary threats are 0.38 LRN, that is lead round nose, and 0.357 semi-jacketed. So the speeds are 300 and 550, and for this they needed a solution. So I explained them that what kind of speed and accordingly how you are supposed to test this. We did few tests with this 2D, 3D, and as in scientific study more of, because weaving these kind of panels is a time consuming task. So scaling up becomes a challenge. And then we performed whatever we have done, a numerical analysis. In this case, he is having abacus. So we performed abacus VU mat programming at our end in the absence of LS Dyna at his place. And then we try to model that we can reach what we wish to, and basis that we targeted that we will give some solution to the Garde, that is the Ireland police force. So these are the 16 layered Kevlar. This is 16 layer Kevlar front and back, and this is the X-ray, and this is a 16 layer ultra high molecular weight polyethylene front back and a X-ray. So you see, because of fibrillation, this white part is actually the lead core of the projectile. It is non-uniformly damaged. Whereas in case of UHMWP, a petaling phenomena, a flower formation will happen because the fibers will stretch. Whereas fibrillation and damage is a uncontrolled, non-uniform kind of a phenomena. Stretching is a uniform phenomena. And all the bullets fired by 0.38 LRN, that is 300 meter, were stopped, and all 550 meters we couldn't. With this case, then we tried with a hybrid version of 8 layer Kevlar and 8 layer PE, front Kevlar or back Kevlar. In both the cases, interestingly, results were different. However, we restricted ourselves to 0.38 LRN at 300 so that all bullets can be stopped. And you can see, though the exit velocity is zero, the BFD, back phase deformation, for one combination is relatively less compared to the other one. I'll come back to this. PE at the back because it stretches well, and Kevlar because of fibrillation absorb the energy fast. So for that reason, the BFD here was less. This is what happens when we cut this material with water jet and see where is my lead bullet and how much damage it has produced. So we see the damage, delamination, fibrillation, fiber failure. The delamination planes in UHMWP are always multiple compared to a single large one in case of Kevlar. So these studies gave us a bit of confidence, and then we thought of having a 24 layer system basis our past studies. Still we found the same, that 550 meters is beyond discussion and it will perforate. So it does perforate it. However, for 300 meter bullet, that is 0.38 LRN, the BFS came down significantly. The projectile was damaged significantly because of higher number of layer as demonstrated in this X-ray image, and these petals remains the same for the PE side or the pure PE thing. And then we did a hybridization of the two, that is Kevlar 12 layers and PE 12 layers, and the X-ray of that. And again, the same results, that we may slightly handle the residual velocity to a lower numbers, but stopping is not done. But then the other one is completely was and it continues to stop. But we could find that what kind of damage, shear plugging, fibrillation, stretching, those are the things which academician or a researcher is interested in. So these are quite good studies that can be done for a variety of existing as well as newly designed materials. And this is how the damage propagates. And this is shows how the damage happens when there is a residual velocity. So in case of Kevlar, it is fiber crush, shear plug, shear failure and fibrillation. Whereas in this case, the fiber crush and the way it is happening and the lamination plane are significantly different. For hybrid system with the front of UHMWP and with the front of Kevlar, the things are slightly different, and that is the reason that your residual velocities were slightly varying. But this kind of hybridization, we can develop better solution. So we could conclude that this was the important thing was that this was the first study using the helium for ballistic application, and thankfully we could give this slide as a solution to the Ireland police. That is, we can stop all the projectiles fired, 0.38 LRN at 300 meters per second, and we have got these many weight possible solutions without any perforation and at a very low backface signature. This material being recyclable and room temperature processable, so the manufacturing cycle becomes very comfortable. And hybridization of Kevlar and UHMWP has led to a better solution, as in having 6% higher V50 than the reverse arrangement. For the time reason, I'll have to move slightly faster and I'll request 5 minutes additional if possible. In my journey, every now and then I come across the term, the world is of drones, but drone may win a moment. It's the rifleman and the tank person who will keep the land. So bulletproofs are inevitable because without a human, you cannot hold your land. For those who are interested in material research, material science, nanotechnology, biomimicry are the key areas wherein one can work along with, for a better future, integration of sensors, self-healing materials. They can be considered as a part of material science. These are the few key things which one can think of. But I am working on now or looking at that we required a even better bulletproofing material, which I'll migrate to the commercial world as well. That I'm looking for a hard strike, fine, a composite core, yes. Then we require a RF and EMI shielding for variety of other devices which are having electronics in it. Then we required a signature resistance, that is your stealth and anti-stealth kind of. So stealth technology is a must in many of the cases along with the embedded sensor. So these are the few areas I am working now. And in reality, the defense to market. Okay, I'd like to directly switch to that these defense composites are no long niche, or at least according to me, they are not, because, or with the help of an example, I would like to take that these technologies can be taken from defense to civil. So these are few of the areas like automotive, energy, infrastructure. They have a similar requirement, but we feel that defense is a different world and civil is a different world. It is not. And with respect to one of the example, that is EV, I would like to discuss. Then battery enclosures, lightweight monocoques, energy absorbing structure. These are few applications wherein the requirements are typically identical. So I would like to take this one, that in defense, what you are expecting from a blast proof vehicle, what we call, that is an example where your defense expertise can be directly utilized for the civilian market. Do we require a high acceleration and maneuverability? Yes. But in EV, we require rapid acceleration capability. It's the same. The maximum occupant protection. Don't we require the passenger safety in a car? It's exactly the same. Minimum weight for maximum performance. Don't we require the largest possible range per battery charge? Or we call it as optimization of. Here we are looking for ballistic and bullet and blast resistance. Here we are looking for the crash worthiness. I'm sure everyone here knows the NCAP rating for the automobiles. Here we talk of long operational endurance, and on the other side we have extended driving ranges. So all in all, whatever is there in the defense world, in some or the other form can be translated into the commercial world also. So that is how we can map between the defense to the commercial world, and that way a technology developed can be utilized for betterment of more. And how I call as my journey, that you can get a problem, a new, a unique, a real world problem from the defense world, and it's the duty of academia to come up with a innovative, real new solution. In our case, it would be material and manufacturing kind of a related technology, and it is the duty of the industry to develop this material or this system or the facility for masses to use. And the real enablers will be you, who can develop the new material systems, because your conventional materials and metals are not going to suffice or do the needful. So it is where DIA, that is Defense Industry Academia, when they work together, then only we can have a real impact for a better tomorrow. So with that, I conclude and I offer from my side that I am on a mission to develop a new generation of engineers who are keen and interested in developing new material and manufacturing solution. So whosoever is willing in that domain is most welcome. And I'll be happy to come down to your place and support you. Okay, good.
Thank you, sir.
So with that, the floor is open for questions, and I know I've had to skip a bit towards my second half of journey. You can ask me anything.
Thank you, sir. Thank you for your valuable session. I would request to the participants to ask
Hello,
your
sir.
query.
Hello,
Yeah,
sir.
please go ahead.
Sir, this is Dr. Arun Kartikin speaking here, sir.
Sir.
Sir, actually, I want to tell you it is a wonderful presentation, sir. So each and the crystal clear explanation about the slides, each and every slides. Thank you so much for giving this knowledge to us, sir. So now we are understanding what is the importance of this composite, actually. So we are adding two or more materials. By the way, we are making so many things, but if it is a form of applications, it is a completely appreciable, sir. In this way, you are great, sir. Thank you so much. Yeah, sorry. So, what are the stages? I mean, what are the stages you have? I mean, cross sir, actually from beginning to that end, permissions and yes, fabrication point of view, everything.
I didn't get exactly the question.
Yes, sir. Actually, if you are testing with bullets and other things, we have to get the permission from different officials. So, how you were overcome from your all the struggles,
Okay.
sir?
Okay, let me put it in a simple way. A designer is the person who will design somewhere, doesn't matter where in the which part of the globe. You need a manufacturing facility wherein you can manufacture this. So even if you are making a simple casting of a metal or anything, and while testing, you have to go to either policing department or the defense department, that is army. So in case of India, it is TBRL, Terminal Ballistic Research Laboratory, Chandigarh is the place where you can get your products tested.
Okay.
And there is no as such permission involved. You have to get the date from them that we have developed something and we need to get it tested. And being
Okay.
academia, they will help you out, of course, on the chargeable basis and government protocol. So it takes a bit of time. And that is where I said that we developed a facility wherein under the single roof, we design, manufacture, and test. And I did it
Oh.
in a time of 9 hours, whereas in general, in countries like India, where civilians are not supposed to carry the weapon, the typical time
Mm.
is 6 months to 1 year.
Oh, so it's very okay. Okay, sir. May I know what kind of machinings you have used for cutting off those materials, those
Water jet,
composites, sir?
water jet,
Water
abrasive
jet
water jet,
machine.
and water jet is the best machining tool to cut any of the composite because lasers burn. Any physical tool will lead to fiber pull out. So
Oh,
water is the best possible alternative. And anyways, I mean, I'll be happy to help in that case. At both my
oh,
locations, I have water jet.
okay, sir. In case of it is a Kevlar fiber means it is difficult to do with that machining, sir. I think Kevlar
Any
based fiber.
fiber thing, if you touch a physical tool, you are going to pull out the fiber.
Okay.
Any energy related thing, high energy, electron, I mean these are non-conducting, so you are bound to go for either a CO2 or a solid state laser. You will have a charred surface, a burnt surface, because of
Okay.
high
Okay.
temperature. So
Ah,
again,
okay.
that's a problem. So water is the best medium because it acts as a coolant as well. Only thing is you need to understand the parameters.
Oh. Okay, sure, sir. Thank you. Thank you, sir.
Yeah, okay, so we are getting few questions on the this side as well.
Good evening,
uh,
sir.
yeah,
Sir, I am Nilesh Gaikwad from Nasik, Maharashtra. I
sir.
have researcher on that same topic, and I am very really appreciate for your session. Uh,
Mhm.
so my question is that, sir, is gas gun test is useful as a ballistic test?
Uh, yes, as far as research is concerned, and no, as far as delivering the solution is concerned. Now, let me complete this. When we are writing a research paper, developing a new product, your gas gun will always be a smooth bore. So, your
Okay.
projectile will be moving in a straight line, and there is no real world obstacle. A bullet fired using any of the weapon except the pistol or the pocket held weapon, it will have a grooving. I mentioned in my
Okay.
presentation in the early part that your AK-47 is spinning at a speed of 2900 plus RPS. That is not possible with the gas gun. So for that, we have to go to the authorized test laboratory who can fire as per the standards. The standard in case of rifle is say 10-meter distance. For 9 mm, it is 5 meter. So, but you have to start with that only. Going directly there and then coming every time with a failure makes no sense.
Okay, sir. Thank you, sir.
Okay, someone mentioned, I'll take one of the texted question. Different angle, what happened? In case of 9 mm, we make a circle of 100 mm at the center of the panel and perpendicular uh, 30 degree, 60 degree and 30-degree shot, 45-degree shots are fired. So these are a part of it. Sometimes it happens that though seemingly perpendicular bullet has to travel the minimum distance, but an angle bullet may perforate because in case of fiber, it is more about if friction is low, the bullet can push the fibers left and right and can make a path. So there is a test standard for that as well. The next texted question is moisture will play a role in water jet machining. Yes, if your pressure is low, instead of completely penetrating the specimen, the water will try to delaminate the specimen. So we should know that what is the thickness of the composite. I mean, you have to do a couple of iterations or you have someone in your team who knows. So let's say my composite is 4 mm thick and my pressure is hardly few hundred of bars of pressure, then you are actually delaminating the panel instead of cutting it. This Amit Pal, if you have anything to mention, you can. I've answered your thing though. You require relatively much higher pressure. If not, then delamination will happen or water will seep in.
Thank you, sir.
Any other question?
Any other questions? Participants, if you have any other question, please ask.
Sir,
Yeah.
have you explored any acoustic applications for this particular composites? Because the same energy absorption principle is there.
AE is more of a, at the time of bullet hit, I mean, I have that, but in case of bullet firing, we couldn't because this thing is done at TBRL and we have the equipment in our lab. So it's more of a PAUT, ultrasonic equipment that will tell us that the panel is uniform or not. If it is with ceramic, we prefer X-ray or CT scan. Acoustic is like when your bullet is hitting, how much, what kind of damage. For that fraction of a second, there will be a significant damage. So I haven't done any experimentation with that till date, but that is something which definitely can be looked at. But I am pretty sure that for that fraction of a second, there will be too much of noise. So how to interpret that data? That would be interesting phenomena. But till date, I haven't seen any such thing. What is the repeated impact on the composite made bulletproof jacket? Okay. Okay, there are two things. When we say 6 to 8 bullets, the rule as per BIS and as per NIJ is every two bullets will be at least 51 apart, that is 2 inches from the edges as well as in between the bullets. The distance has to be at least 51 part 1, if this was the question. Part 2, what happens if a second bullet hits on the same spot where the first bullet was? No one can design a bulletproof system for that, because in that case the weight penalty would be infinite. If a single second bullet can come on the same place, then third can also come, so there is no end to it. So the standard testing protocol is 51 apart. This is a standard. People do experiment with 25 and 20 That is good for research, but the test laboratory, they always test at 51 plus millimeters. Okay, thank you. Feedback. Is there any other question?
Okay, so there is no other question from the participants. Thank you, sir. Thank you for your wonderful session.
Sir, one question, sir.
Yeah.
What's the weight of the armor, sir? Weight of the total armor?
When we started the journey, India was at 10.4 kilogram bulletproof jacket for Indian Army to stop AK-47 projectiles from our north and the top kind of the international border location. And we could bring it from 10.4 kg to 8.2 kg. Is that clear? So 21+% of weight saving in that. And for sniper thing, there was no solution globally available which can stop 6 rounds of sniper, and we could deliver a solution, and that was for 9.5 kg. And that is being transferred to 3 units, Medhani public sector and 2 private.
Okay, sir. Is there any energy absorption study done, sir?
Yes. But 90 minutes is too less a time.
Okay.
Yes, we have done that. Energy. So we measure the force at the back and we have calculated the energy absorbed by the panel and transmitted to the body. So your question is very relevant. Even if the bullet is stopped and this 3000 or 2000 joules of energy, what kind of effect it will be? So it's like a child hitting a punch on a let's say a 50 kg or a 70 kg human versus a fighter kind of a WWE champion hitting a punch on the same 50 to 70 kg human. And now we're talking of much higher weight. So yes, we did right.
Thank you, sir.
Okay, thank you, sir.
Can carbon fiber, okay, very relevant question, sir, if permitted. Amit, sir.
Yes, sir. Yes, sir. Please, sir.
Can carbon fiber composite made easy to bulletproof? Okay. Very good question, sir, and thanks for reminding. Carbon is not a ballistic material. So, looking at the elastic modulus of carbon fiber, Those who come theoretically, they feel that I can design it for 1.5 and 2.5 kg jacket. But unfortunately, at high strain rate, carbon do not behave in the ballistic impact. So your jacket is bound to fail miserably and there will be only shear plugging of the bullet. So we knew it. It's very well documented as well. So there is no point. The only location we can think of carbon fiber is at the end, that is towards the SEP or at the end of the hard armor panel. Even there, since we are already using UHMWP, so there is no much point. So we are not using. But in the soft armor panel thing, there's a Korean company who is making that, and there are few more now. I think DuPont as well, maybe. So a hybrid of Kevlar and carbon to act as a back face. We call it as a trauma attenuation pad. The back face deformation has to be stopped. Our basic idea is to increase the area of energy absorption. So you are getting 2000 joules at a point versus a large area. The damage in the tissues will be much less. So carbon will even restrict that if the bullet is completely stopped in a hybrid combination with Kevlar that is being used. But individually, carbon is not a ballistic material. I hope I answered your question. Is there any sunglass bulletproof composite? Okay, it's not glass, it's a 40 polycarbonate which is being used as a bulletproof material. All your VVIP vehicle, which we call as a bulletproof vehicle, they have got front and back and all four windows. That all glass is basically a polycarbonate. And depending on the threat level, what threat we want to protect, so it's a mass versus threat. How much you want to give the protection, accordingly you increase the thickness of the polycarbonate, and that serves the purpose because that's a ballistic grade. I'm sure you must have seen, at least in the photos and videos, the policeman holding a transparent kind of a sheet. That is a polycarbonate because that is an impact resistant material. So better grades of that, of course. Okay, if
Okay, sir. Thank you.
any solar panels are required use for nighttime useful for defense. Can you please explain me the question, Amit sir?
Any solar panels are required used for nighttime useful. I think if Venkateswara Rao sir is present here, please unmute yourself and ask the question.
We may use silicon carbide and silica materials for the solar panel development. For this purpose, can we add the same application for the armor jacket?
Silicon carbide, you said?
Yes, sir. Silicon carbide along with silica.
Okay, silica, I don't know. I mean, not for bulletproofing, but silicon carbide already we are using for bulletproofing. It's a very good material for bulletproofing.
Yes, sir. Yes, sir. Combining these two materials, we can be able to.
Silica, I don't know, so I won't comment. Developing a silica in itself is a technology. So silicon carbide in itself is a very good ballistic material, blast-proof material. But silica, I don't know.
Yes, sir. Yes, sir. Okay, sir. Okay, thank you.
If someone fire continuously at same spot, okay, same spot in any case. So when you say second bullet, it could be third, it could be fourth. So no infinite weight penalty, not feasible. It's already answered. Yeah. Tavron uses as a material as bulletproof. Yes, Tavron is a brand name. So it's a aramid fiber they are making. DuPont was the first to develop Kevlar, which is a commercial grade by DuPont. The generic or the scientific term is the aramid fiber. So Tavron is producing that family of aramid. Can non-Newtonian material be used? Yes, we have developed a bulletproofing solution using shear thickening fluids. We have vibrant participants. Good. STFs can be used, but till 9 only.
Okay, thank you. Thank you, all the participants, and thank you, sir. I know there are a lot of questions also, but as the time is limited, we have to move to our next session. Thank you, sir. Thank you for the wonderful session.
Okay. Thank you, everyone. Thanks a lot, sir, for giving me the opportunity. And I welcome you all for all the materials and ballistic related research. And more importantly, let's develop the new generation who can come up with the newer solutions. Thank you.
Thank you, sir.